everyone. Welcome to episode number 672 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by me, Amelia Dalton. Embedded systems take center stage in this week's podcast. My guest is Rolf Segger from Segger. Rolf and I dive deep into their extensive embedded solutions portfolio. This includes a closer look at their RTOS, debuggers, IoT offerings, and their distinctive approach to licensing and support. We also explore the fascinating concept of emApps, which represents an intriguing vision for embedded system design and is poised to shape the future of smart device development. So, without further ado, please welcome Rolf to Fish Fry. Hi, Rolf. Thank you so much for joining me.
Well, thank you for having me.
Absolutely. So, Rolf, first, talk to me about Sager.
Okay, so I started Sega about 35 years ago, and we started with just a real-time operating system, and then I expanded with more middleware, MWin, file system, etc. So today we have four different types of products: the middleware, development tools, so embedded studio, and system view, which is more of a system verification tool, and the J-Links and the flashers. And the J-Links and the flashers is what we're most known for.
So, what do you think are the most significant security challenges facing embedded systems designers today?
Well, from a security perspective, yeah, again, we have different products, and some of them contribute to security and others don't. Like a J-Link is primarily a great, probably world's greatest, most popular debug probe, but it doesn't contribute much to security. Yeah, what are the security challenges? I mean, obviously, security becomes more and more important as embedded systems become IoT devices. It used to be you have your washing machine or a coffee maker and it was isolated, and there was no way for it to get hacked. But also, if it got hacked, it wouldn't be a huge problem because at least it couldn't interfere with the internet. These days, if you hack a connected device, you hack a light bulb, it could basically be used as a DDoS, distributed denial of service attack. So securing embedded systems is more important than ever. What do? We have various components. We have emCrypt, which is a complete suite of development of security software, basically a software library, and Secure Bootloader, which is a brand new product that we just came out with, mBoot Secure. It complies with all the modern standards the European Union just came up with, and other countries are probably also coming up with. And in general, obviously, all of our tools are designed to be secure and fit right in.
So, you guys offer a wide range of middleware, including file systems, RTOS, GUIs. So, talk to me about the specific advantages that this kind of integrated approach brings to the table.
Okay, we have a complete suite. We also sell it basically or license it as a complete Empower OS, as a complete operating system. When people who are not from the industry like ask me, what do you do? What is it? I explain it as it's an operating system for embedded devices. It's a bit like Windows for embedded devices, only that it's modular and much smaller. And what do we have? It has pretty much everything that people need. And I'm probably going to forget something, but it starts with a kernel. emBoss, which is the oldest product. So we have a new version of it, emBoss Ultra, which is now cycle accurate and so on. Keep improving it, obviously, but the emBoss Ultra is quite interesting because it's cycle accurate. So you can do delays, like microsecond delays. The other components are a file system, mFile, a graphics software, MWin, emCrypt I mentioned, then USB communication software named mUSB, then mNet for TCP/IP connection, and mSecure, and pretty much everything you need. I'm sure I'm forgetting something, but pretty much everything you need. And the nice thing is everything is obviously is designed, follows the same coding standard, it's designed to work with each other, right? So all the components fit into each other easily, which doesn't mean you have to use all of them. We have a lot of customers using FreeRTOS or whatever, something else, and then still use our file system. Or like if you want to use one component, doesn't mean you have to use all of the other components. They're completely independent of each other. They're very much optimized for embedded systems, meaning they're fast and efficient, very small in code space, but most of all, very, very small in RAM usage. In most embedded systems, Flash is cheaper than RAM. And flash can a lot of times also be easily expanded by like adding more QSBI. RAM cannot be expanded. So they are very much optimized for low RAM usage. And the other big benefit you have, I mean, everything is tested and maintained up to date. It follows all the latest CRA standards, so vulnerability things, you have maintenance. You don't have the problem if you use something that's self-developed and that critical developer leaves, you might lose some knowledge. You use open source. It's not that well tested. They don't do regression testings a lot of time, even though some of the open source things are clearly usable. And then there's stuff that comes from the silicon vendors, and that is all a lot of times also very usable. I don't want to say it's bad quality, but it's probably also not tested as well as our stuff. But there's one very important point. If you use stuff that comes from silicon vendor A, and then you find, well, we'd rather switch to this new chip from silicon vendor B, then that is not so easy because silicon vendor A tries to lock you in. And if you use now the other chip, then you're basically like, oh, we got to develop everything from scratch. With our stuff, it's all nicely structured. So it's designed to make it very easy to go from one chip to another, from one vendor to another. And yeah, what's a typical product? I mean, there is not really that typical product that uses it all, but I can give you one example. Call it here the Flasher. This is the leading in-system programmer. It's not just one, I mean, it's a whole family, but this is one of the latest members is a Flasher Compact, and it uses M-file. So it can store files, obviously, in a NAND flash with a very good NAND flash driver, but I'm not going to get into any detail here. So it uses our web software, so MWeb, so we can connect to it using a web server, even though it only has USB-C, it only has USB. So we have also a piece of software that allows you to connect to a web server via USB, which I find very interesting because a web server, is great for configuration, for looking into your device. You don't need to install any software. So web server is very useful. It can also be done, via USB. What else is in there? Obviously, the operating system is in there. And again, MS Ultra, we take advantage of the fact that we can do cycle accurate timings. In the models with Ethernet, we have the network interface with a model, a portable version that has a graphic display. So we use our graphic software in there. There is no really typical use case. Embedded systems these days tend to be pretty complex and use a lot of software.
Given the rise of IoT and increasingly complex microcontrollers, how is Sager supporting these trends?
Yeah, it's tricky. Basically, the answer is by hiring more people. The world used to be easy. You had one core and some flash and some memory. These days, you have like 7 different cores, and one enables the other one. And you have different types of memory in different memory spaces, and you have security things. You need to open up the chip, trust zone. Everything makes it more complicated, and it's actually a challenge to keep up. On the other side, it's good for us because it means we have to put a lot of work into it, which means other people, competitors, open source also have to put a lot of work into it, which makes it harder for everyone. But since we so much focus on it, I think it gives us a competitive advantage. But it really is a lot of work to support these additional chips. The other thing we do is we make it open, so a software development kit and what we call DSK, the device support kit, so other people can do the same thing. So we can give this to our customers and say, hey, this particular chip, we can do it. It's going to cost X, so we'll do it for free. But sometimes we're busy, or we can tell people if you want to implement this specialty, you can do it yourself. And we give this to the silicon vendors as well, and especially say silicon vendors in Asia and China, a lot of times they like the opportunity to do it themselves. So basically a combination of those strategies. And then we're looking at using AI for some of that stuff. So flash loaders basically tell the AI, here's the manual, give us the flash loader.
We should also talk about licensing and support. So, what's your philosophy on that?
I think our core motto is it simply works. And I look at a smartphone, right? And smartphone is obviously a highly complex piece of technical equipment, but anybody can use it. I mean, I know people who can barely read and write, but they can use a smartphone, right? So it should simply work, and you shouldn't have to open up the documentation. And that's also where we strive to be with our products. So that's easier for the J-Links and flashers. For things like the middleware, obviously, you need to have a programming background, but they are very easy to use. So it simply works is the main thing. But the other thing is fairness. We try to be fair to everybody in the space. That includes employees, but obviously also our customers. And we try to not get anybody into a situation where they depend on us.
So let's talk about emApps for embedded systems. So talk to me about how this approach works and the benefits that it can bring to embedded systems design.
My favorite subject. Okay. As I said before, well, a lot of the products that we have are kind of born by a need that we saw in our own products. And so the operating system I was using initially when I was developing software for different projects, and I saw that I could use the same components or the same kernel in project A and project B, even though they were like two completely different things. So it became clear to me that there is a market for portable software, right? Which is fairly obvious when you look at it. And a lot of the stuff we developed because we figured there's a market for it, but a lot of it we developed because we saw a need for it ourselves. So, for example, in the J-Link, in the flashers, and it's also one of the benefits of our software. We are our own customer, so we use the things ourselves, which is always good to have in-house testing and in-house feedback. So I talked about what products are we using, what software components are we using in the J-Links and in the flashers. And in the flashers and also the J-Links, we saw a need for something like emApps. Challenge is the following. New devices become more complex, but they're always different. Like you have a new CPU, then the flash loader is going to be different. So every manufacturer has something different. And not only manufacturer A has one flash loader. No, every device from that manufacturer is probably going to be different, right? And so we figured early on, and we don't want to continue to modify the firmware of the J-Link or the flasher just because we add a new device. So there are two things you can do. You can either do all the stuff on the PC and keep your device dumb. The downside of that is it's not very efficient because you have links like USB and Ethernet. Let's talk about USB. USB is fast these days. USB 3 has, I'm not even sure what is it, 3 gigabits or something. It's super fast. What USB isn't is it has a latency. So it's not super fast when you transfer small packets. It's optimized for high data bandwidth. So if you want to transfer by multiple megabytes high bandwidth, it's very good for that. It's not so good when you have a lot of small packets. So when you have a chip and you basically have to tell the chip, hey, write to the so-and-so register, and then read the other register, finding out if the chip is ready, and then write again, then you have a lot of small transactions. With a lot of small transactions, high latency link becomes a problem. So if USB 2 is better than USB 1 in that sense. USB 1 had like a 2 millisecond latency. USB 2 has less microframes, but call it roughly 250 microseconds. Let's just say every transaction roughly takes, depends on the hub and stuff, but roughly takes 250 microseconds. Means you can now do 4,000 transactions per second. So if you want to write something and you write one item and then you have to say, are you ready? Before you can write the next one, the best you can do is 2,000 bytes per second. And that's not a whole lot, so that's slow. So if your variable intelligence is in the PC, then that slows down what you can do. So it's much better to have the intelligence further down. So have the intelligence in the unit itself, in the J-Link and the flasher. Combine that with we don't want to modify the firmware. We need to be able to download programs. And the next thing is, well, we're using different processors in these things. We're using primarily ARM processors, but we don't want to be locked to ARM processors. So we came up with the idea of having our own virtual processor, and that's what emApp does. And we use that in the J-Link. Just take the J-Link, be it for flash loaders or for other logic. Let me give you an example where the USB latency is also a problem. Say some devices have it, like after reset, you need to unlock the device, but you only have 100 microseconds time. Obviously, if you have a USB link that takes like 300 microseconds, you're not going to get there. So the PC cannot do it. So you need to have a program running in the probes that basically says, do a reset release, check if the device has waken up, because once you release reset, it doesn't immediately wake up. There's a delay because of capacitors. So you're now reading, say, the ID register, and as soon as you get the right ID register value, now you can say, okay, let's do the particular write and bring the device in a particular state. Because the timing window is so small, the PC can't do it, and you don't want to put in the firmware again. So you need something like embedded apps. So there's a variety of reasons for where it's useful. And especially in the flasher, we found it extremely useful because we use it for the flash algorithms. But we're also now using it for many more things, like communication, for example. Units that have Ethernet, you can have your own server. We can have things where, as I said before, the flashers have a web interface. So you can connect via a web browser, you can transfer files. It's actually really neat. You can see what's going on, you can configure it, you can also control it. You can say program, you see the progress bar and everything. Problem with that web interface is different customers want different things. Let's take a simple example. You have a big manufacturer in Vietnam, and they're like, well, our people don't speak English. We would like this in Vietnamese. If they buy two flashers, we basically tell them that we're sorry and we can't make that change, right? If they talk about 500 of them, we'll be like, well, let's see what we can do. But then again, we don't want to add 20 different languages. Plus, you can't keep everybody happy. It's like building one car and expecting the whole world to be happy with that one car. It's not going to work. So if we put the web server in an application, we can basically say, hey, here's the web server, and you do with it whatever you want. And emApps, the virtual processor, it runs in its own address space, which means whatever these people now do, whatever they program, if they make a mistake, it can't crash the system, right? It runs in its own memory space, and every memory access of that virtual processor is monitored. So we basically check, is the access outside of the memory space that we've given you? So the app requires a certain amount of memory. Only the app knows how much. So the app will tell us, I need whatever, 64 kilobytes. You get 64 kilobytes. If now that particular app accesses something outside of its own memory range, it's the same thing as an app on your PC, on your phone. It basically, the operating system stops it, right? Meaning the emAct, in this particular case, the executor basically stops execution, returns to the caller, and the caller now can figure out what to do. It can run like a backup app but it makes sure no harm is done. So the nice thing is you can give this to your customers or to anyone. They can extend it, they can modify it. It's a great way to customize an application. It's a great way, and we can talk about a lot of other applications. We can give this into the hand of the customers, and the customers can customize the unit. Like one other example that I would have is, let's take a water maker. I have an RO system here, and I want my RO system, so my water maker, to be in sync with battery charging. So my house runs on solar, and ideally, I want the water maker to run when I have enough energy. So I would say something like, well, if we have enough energy, then fill up the tank. And if it's low, then only fill it up if you need to. And you can do that and program. So I have a little embedded unit that controls it. And you can do that with tables and say time-based and whatever. But it's difficult. It's much easier if you can write a little program that basically says every time, periodically or whatever, that basically takes the time of day and maybe the battery voltage and maybe the amount of water, the percentage in the tank into account and makes a decision. So you can write a little program that does that. It just adds flexibility to embedded devices. And it's completely safe because everything runs in a sandbox. And what API, what you allow as a manufacturer, what you allow to these applications to do entirely depends on you. You give it an API and you can say, hey, you can only switch the LED on, or you can switch the water maker on. Or you can say, hey, you have access to Ethernet. You can send Ethernet packets, or you can only send so and so much. Or you can say, hey, you can access the storage, or you can only do read-only storage. Whatever you do, whatever you define, it's entirely up to you. And you can also say different apps have different rights. Say, for example, an app that is signed and comes from the manufacturer can do all of this, or an app that comes from the customer can only do this and that. So there's a lot of stuff that can be done. These apps are extremely small. I mean, I'm a big fan of these. We keep encountering more and more things, and we take more and more advantage of what can be done with these apps. So it comes with its own compiler for a virtual processor. And we just put the compiler online so anybody can just try out the compiler, which is pretty cool. We have a source code on the left, output on the right.
Nice. All right. All right, Wolf, it is time for your off-the-cuff question. So, if you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there, what would you have?
That's a dangerous question. If I had one meal, I'm quite happy where I am. I live in the Bahamas happily. So I would I'm a simple middle of the road guy. I would probably just go to my favorite Italian restaurant here.
There you go. That's nice. Awesome. Well, this was super cool. Thank you so much for joining me, Rolf.
Thank you so much for having me, and let's do this again.
Well, folks, that's all I've got for this week's Fish Fry. But if you'd like even more information about Segger, I've included a slew of links below the player on this week's Fish Frying page on eejournal.com and in the description for this week's YouTube episode as well. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If LinkedIn is your thing, I dig it. You can follow us or me on LinkedIn, and we are also on Blue Sky Social and Mastodon too. And we have that YouTube channel I just mentioned, youtube.com/EEJournal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series hosted by me. And of course, you can subscribe to our EE Journal YouTube channel as well. Thank you, everyone, for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's AMELIA, at eejournal.com, or post a comment on our forums on EE Journal. For the week of March 6th, 2026, I'm Amelia Dalton, and you've been fried.